Welcome dear learners. We are continuing Unit 1 Chemistry as a Science Discipline and Scientific Analysis. In the present module, we are focusing on standard deviation in analytical chemical data. In this module, we are focusing on average deviation, which is to recall the previously studied concept, standard deviation, illustrative examples of average deviation and standard deviation, relative standard deviation, and numerical problems based on average deviation, standard deviation, and relative standard deviation. First of all, average deviation. In the last module, we discussed about mean, median, and average deviation. Here we are taking average deviation to recall the concept because it is very essential to study the next step, that is standard deviation. So, in order to understand the concept of standard deviation, we have to recall average deviation and the concepts first. So, average deviation. The average deviation measures the dispersion of data around the mean. That is, in order to find out the average deviation, we have to calculate the mean of given set of data first, and this average deviation express the dispersion of the data around the centralized mean. You know, the average deviation can be calculated by using this expression. It is very well clear that the numerator represents sum of absolute deviation. What do you mean by the term absolute deviation? You have studied it. Absolute deviation simply represents the modulus of the difference between individual measurement and the mean of the measurement. So, xi represents individual measurement and x bar represents the mean of the data. So, the modulus of xi minus s bar is called absolute deviation. Here, xi minus s bar modulus is the absolute deviation. You have to sum this absolute deviation and divide it with the total number of measurements to get average deviation. That is, the expression for average deviation is sigma modulus of xi minus s bar divided by n, that is nothing but total number of measurements. Now, the average deviation quantifies the precision of a data set. It is very well clear that a smaller average deviation indicates more consistent measurement. You are very much familiar with the term accuracy and precision. Precision indicates the repeatability of data in a set of measurements, the closeness of different values whenever you are performing more than one analysis. A smaller average deviation indicates more consistent or more precise measurement. This average deviation is practically valuable in evaluating the repeatability, that is nothing but precision of experiments. Now we can illustrate average deviation by taking a simple example. This is also to recall the concept you have studied in the previous module. So, suppose you are titrating an acid with a base and obtained the following volumes of titrant, which is in ml, to reach the end point. The terms titration, acid-base titration, end point, etc. are very popular to you because you learned it in your plus 2 classes about volumetric analysis. Here we are finding out the concentration of a solution by titrating it with another solution having known concentration, exactly known concentration. Now, in this titration experiments, the analyst got, or suppose you got, these sets of values, and the sets of values are here. In the first experiment, you got a volume of 25.1 ml. In the second set, you got the volume as 25.3. Next set is 24.9. Another two sets are 25.2 and 25 ml. So, you got 5 different volumes whenever you are finding out the volume in a volumetric analysis, which is obtained at the end point of the iteration. Now you have to calculate the average deviation by systematically proceeding to the following steps. In the first step, you have to calculate the mean of all these set of 5 values. Mean x bar is calculated by simply adding all these values and divided with the total number of measurement, and the total number of measurement here is equal to 5. So x bar, that is equal to 125.5, which is the sum of all these values, divided by the total number of measurements, that is equal to 5, and the value obtained as mean or average is 25.1 ml. You have to remember this value 25.1 ml as the average of set of measurements. Now proceeding into the second step. In the second step, you have to calculate absolute deviation. I mentioned it previously that absolute deviation is the modulus of the difference between individual measurement with the average or mean. The mean value is 25.1, so you have to take the difference between individual measurement with the mean and takes its modulus. So you can calculate absolute deviation by using the expression. It is the modulus of xi minus x bar, and on calculating the absolute deviation in 5 set of measurements, you will get the data like this: 25.1 minus 25.1. The second 25.1 is the x bar, that is the mean. The first 25.1 is the individual measurement. So here there is absolute deviation is equal to 0. And since it is a modulus, you have to consider only the difference, only the magnitude of the difference, because such deviation is called absolute deviation. So you have to find out absolute deviation in the 5 set of measurements, and the set of data are here. Now, in the third step, you have to finally calculate the average deviation. The average deviation can be calculated by the expression. Average deviation is equal to sum of modulus of xi minus s bar divided by n. Remember, n is the total number of measurement, that is equal to 5 here. And in the previous slide, you got the values of absolute deviations, and sum that absolute deviation, divide it with the total number of measurement to get to the average deviation, and the average deviation is equal to 0.6 divided by 5, and that is equal to 0.12 ml. So the average deviation of these 5 sets of volumes, 5 sets of data is equal to 0.12 ml. The average deviation indicates that on average each measurement deviates from the mean by 0.12 ml. This is the most important significance of this average deviation. Average deviation, as I mentioned earlier, it simply represents the dispersion of the data around a central mean. So this value 0.12 ml clearly indicates that each and every data has a deviation of 0.12 from the center or from the mean. Now, the most important statistical procedure we adopt in quantitative chemical analysis is here, that is nothing but standard deviation. Standard deviation is abbreviated as SD, and this about the standard deviation. In analytical chemistry, one of the most common statistical terms employed is the standard deviation of a population of observations, of a set of observations. It measures the spread or variability of a set of data around the mean. As I mentioned in the case of average deviation, in the case of standard deviation also, it represents the spread or variability of a data set around a central or a particular mean. And it is particularly useful, that is the standard deviation is highly useful in determining the precision and hence reliability of experimental results. Precision simply indicates the repeatability of set of measurements, repeatability in values of set of measurements, and it is useful in determining the precision as well as the reliability of measurements. This standard deviation helps to evaluate how closely repeated measurements are clustered around the mean. lower standard deviation or a low value of the standard deviation indicates higher precision in analytical measurements. Large deviation from the mean may indicate experimental errors or the presence of outliers which can then be investigated further. Population and sample standard deviation. It should be noted that there are two kinds of standard deviations. They are in the title itself, nothing but the population standard deviation, abbreviated as sigma, and sample standard deviation, abbreviated as S. These two terms are highly useful in statistics. In many cases, in quantitative chemical analysis, we are giving emphasis to the second category, that is nothing but sample standard deviation. First of all, we have to differentiate these two kinds of standard deviation, how they are differ. They differ even in their expression also. We can enter into the details of the expressions for these two kinds of standard deviations, namely sigma and S. Both of these measurements, that is both the population and the sample standard deviation, measure the degree of dispersion in a given data set. The population calculates all values in a data set. The sample standard deviation, however, calculates values that are only a part of the total data set. This is the core difference between the population standard deviation and the sample standard deviation. Moreover, these two standard deviation differ by the expressions also, and these are the expressions. First of all, formulae of population standard deviation, that is sigma. Sigma can be calculated, or population standard deviation sigma can be calculated by this under root sigma xi minus mu square divided by n, where mu is known as population mean, that is mean of a set of measurements. The second one is sample standard deviation, which is abbreviated as S. This is the expression for sample standard deviation, and the sample standard deviation is given by under root sigma xi minus s bar square divided by n minus 1. Remember, in a set of small measurements n, the denominator you have to note it, it is n minus 1, not n. In a set of n measurements, in order to calculate the sample standard deviation, we use denominator as n minus 1. But however, in the case of population standard deviation, the denominator is n. So, the second one stands for sample standard deviation, and in this expression, x bar is the sample mean. However, in the previous expression, mu is there, where mu is the population mean. So, in the population standard deviation, we are using mu, that is population mean, and in sample standard deviation, we are using x bar, that is nothing but sample mean. So, these two are the expressions for population standard deviation and sample standard deviation. This you have to remember always, and more frankly we can say like this: in analytical chemical measurements or in quantitative chemical analysis, where the total number of measurements are minimum, we are commonly using the second type, that is sample standard deviation S. Sample standard deviation S is given by the expression under root sum of xi minus s bar the whole square divided by n minus 1. Now, illustrative examples. We can illustrate the concept of standard deviation, preferably the sample standard deviation, with some examples. Example number 1, a chemist performed 5 replicate measurements of the concentration of a salt solution. He is provided with a salt solution and he has to measure its concentration, and he performed some analytical measurements and got the data, and the concentration is in milligram per liter. these are the values obtained by the analyst, and the set of values are total 5, and the values are here. In the first case, he got the value 50.1 milligram per liter. The second value is 49.8, third one is 50.3, fourth one is 49.9, and final value is 50.2 milligram per liter. And we have to calculate the standard deviation of these 5 set of data. For this, we have to calculate the mean of these data set first. That is, we have to compute x bar first. So, x bar can be calculated, or mean can be calculated. Sample mean can be calculated by the expression. You take the sum of all these values divided with the total number of measurement, that is n, and s bar in this measurement is 250.3 divided by 5, and that can be represented as 50.06 milligram per liter. So, remember this value 50.06, that is the mean of this set of data. And in the second step, you have to calculate deviation from the mean. So, you have to compute xi minus x bar. For each set of measurement, subtract the mean to get xi minus s bars. That is, you have to subtract mean from each set of data set. You are having 5 set of data, and you are having the mean value, and you have to deduct or subtract mean value from each set of measurements. Like this, you are getting the final result. 50.1 is the individual measurement, minus 50.06, that is the average or mean. You go to 0.04, and in the second case, there is a negative. In average deviation, you have to keep in mind, you are there taking the absolute deviation. So, you are considering only the modulus, but in standard deviation, you have to take the difference. So, the difference is 49.8 minus 50.06, that is minus 0.26. So, in all the cases, you have to subtract the mean from the individual measurements. So, you are finally calculating xi minus s bar in each sets of data. In the next step, you have to square these deviations. So, you calculate the deviation in the second step, and you have to take the square in the third step. Square the deviations to get xi minus s bar, the whole square. So, these are the square of the deviations. So, the square of the deviations are definitely the positive quantities, because the square of a negative term is also a positive term. So, here all these values are positive quantities. And in the fourth step, you have to calculate another important factor, that is called variance. Variance is a square. We will come to more details of variance in coming modules, and variance is simply the square of the standard deviation. So, in order to calculate the standard deviation, in the fourth step, we are generally taking the square of the standard deviation, that is S square is calculated. S square is nothing but the variance. So, the fourth step is the calculation of the variance or square of the standard deviation. And in the final step, we have to take the square root. The square root of variance is nothing but standard deviation. So, in the fourth step, we are calculating the variance, that is nothing but S square. S square is calculated as sigma xi minus s bar the whole square divided by n. This is called the sample variance, because the square root of which gives the sample standard deviation. So, the variance in the present quantity is calculated as S square is equal to 0.043 milligram square liter square. You know the unit is squared. The unit is squared. The actual unit is milligram per liter. So, here you are calculating the variance. Variance is the square of the standard deviation. So, the unit is also squared here. And finally, we are coming to the last result, that is nothing but the standard deviation. Yes, you know standard deviation is the square root of the variance, and the standard deviation is square root of variance, and you can calculate the variance already. You calculate the variance already, and you have to take it as a square, the square of which, that is square root of 0.043, that is 0.207 milligram per liter is the standard deviation. So, standard deviation S is square root of S square, and S square we already calculated, that is variance is equal to 0.043. It is the square root gives the value of standard deviation, that is 0.207 milligram per liter is the standard deviation of the given data set. And on a concluding remark, we can say that the data points deviate on an average by approximately 0.207 milligram per liter from the mean concentration. So, standard deviation also represents the dispersion of the data from the central mean, and here the deviation from the mean is 0.207 milligram per liter. Now, this is another example to illustrate the concept of standard deviation. It will give you more clear idea regarding the practical calculation part associated with the standard deviation. This is the situation. A chemist is determining the concentration of an acid solution using a titration experiment or volumetric analysis experiment with a standardized sodium hydroxide solution. In 5 replicate titrations, the volume of NaOH used are as follows, or the titer values are here. These are the 5 set of data. The data values are in volumes in ml. First data 24.85, second one 24.80, 24.92, 24.88, and the final value is 24.90. So, you have to compute the standard deviation of these 5 sets of volumes, and we can proceed in a systematic way as in the previous problem. You have to calculate the mean of the data, and the mean is calculated by using the expression. You have to sum all these values and divide with the total number of values, and S bar of the set of data is equal to 124.35 divided by 5, that is equal to 24.87 milliliter. You have to remember this value. This is the mean. This is most important, and this standard deviation represents the dispersion about this mean, about this central mean, that is 24.87 ml. Now, in the second step, you have to calculate deviation from the mean. Deviation from the mean can be calculated as xi minus s bar. You have to take each individual measurement and subtract the mean from that value to get the mean from deviation. And in the third step, you have to square these means, and the data obtained is xi minus s bar, the whole square. These are the square of the deviations, and in the next step, you have to calculate variance first. You are very well familiar with the fact that variance should be calculated first, then take its square root to get the final standard deviation, because standard deviation is the square root of variance, or simply variance is the square of standard deviation. So, in the fourth step, we are computing variance. Variance is S square equal to sigma xi minus s bar, the whole square divided by n minus 1. This is called the sample variance, and in the present problem you will get S square as 0.0022. In the final step, you have to compute the standard deviation, which is the ultimate aim of this example. That is, standard deviation is the square root of the variance, and on this S equal to square root of S square, that is square root of 0.0022, and the final value is 0.0469 ml. This indicates that the standard deviation of a given set of 5 volumes equal to 0.0469 ml. This means that the volumes used to reach the end point deviate on an average by approximately 0.0469 ml from the mean volume. This about the concept of standard deviation, its illustration. Now, what are applications of standard deviation in analytical chemistry? Comparing method. Standard deviation is used to compare the precision of different analytical methods. This is one of the most important application of the standard deviation. Another one is error propagation. When combining multiple measurements, the standard deviation helps to estimate the overall uncertainty of the results. That is, it is possible to evaluate the error propagation by using the concept of standard deviation. Now, reporting uncertainty. Analytical results are often required as mean plus or minus standard deviation, providing an insight into data reliability. So, standard deviation can be used to express the uncertainties in reporting the measurements. Repeatability studies or analyze precision is another important applicability. When conducting repeatability test standard deviation indicates how consistent results are under identical conditions. So, it helps to evaluate, it helps to indicate precision in a set of measurements. Now, another important concept, another important statistical procedure which is related to standard deviation, that is nothing but RSD or relative standard deviation. We are now focusing on the concept of relative standard deviation. Relative standard deviation, abbreviated as RSD, is another measure of precision. As in the previous case of standard deviation, this RSD is also an indication of precision or reliability of a set of measurements. This RSD is particularly useful in analytical chemistry for comparing the precision of data sets, especially when their means different, when these analysis means differ significantly, or if there is significant deviation in mean value, then we are taking RSD to evaluate such difference, to such deviation. The relative standard deviation is the ratio of standard deviation to mean. This is very important as far as the definition of relative standard deviation is concerned. The relative standard deviation, RSD, is a ratio. It is the ratio of standard deviation to mean. That is, RSD can be calculated as standard deviation divided by x bar, or standard deviation divided by the mean of the set of measurement will give relative standard deviation RSD, or simply RSD equal to SD divided by x bar. Now, this is an example to illustrate the concept of relative standard deviation. The concentration of a solution is measured 5 times and the given data are shown here. 10.1, 10.3, 10.2, 10.4 and 10.2 milligram per liter is the concentration obtained for a solution by an analyst, and we have to calculate the relative standard deviation, and we have to proceed in a systematic step. The first step is necessarily the calculation of the mean. You have to calculate the mean by adding these values together and divided with the total number of measurement 5, and that is equal to 10.24 milligram per liter. That is the mean of the data. And in the second step, you have to calculate standard deviation S, and standard deviation S can be calculated as in the case of the previous example. We illustrated the case of the standard deviation. You can calculate S in the present problem also, and S is equal to root of sigma xi minus s bar the whole square divided by n minus 1. Look, the denominator is n minus 1. N minus 1 denominator simply indicates that you are dealing with the sample standard deviation, and in analytical chemistry we are generally considering the sample standard deviation, and we are not taking the population standard deviation. You are familiar with the difference also, and S can be calculated in the present problem by using this expression. The sample standard deviation of the present problem is 0.114 milligram per liter. Now, you have to arrive at the final result, that is RSD to be computed, and RSD, as you know, it is standard deviation divided by mean of the measurement, or RSD equal to SD divided by x bar, and this in the present problem x bar is previously computed as 10.24 and standard deviation is 0.114. So, you have to divide standard deviation with the mean of the measurement, that is RSD equal to 0.114 divided by 10.24, that is equal to 0.0111. This is the relative standard deviation. Now, it is possible to express relative standard deviation as a percentage. That is, relative standard deviation can be multiplied with 100. In that circumstance, when relative standard deviation RSD is expressed as a percentage, it is termed as coefficient of variation. That is, coefficient of variation CV is RSD percentage. That is RSD multiplied with 100. That is CV equal to RSD is SD divided by S bar. It just multiply with the 100. That is CV equal to SD divided by X bar in discussing some numericals and simple MCQs based on the concept we have learned so far in this module, that is about relative standard deviation, average deviation, etc. We can now enter into the problems. This is the first MCQ. In a titration experiment, the volumes of titrant used were 20.2, 20.0, 20.4, 20.3 and 20.1 ml. The mean value is 20.2 ml. What is the average deviation? So, in this problem, the mean of the data is given, the data is also given. These are the options, and you have to calculate the average deviation and pick out the right option from this given data. So, the answer to your problem will be option B, that is 0.1 ml. And the question arises, how you can arrive at the average deviation. Average deviation can be simply calculated by using the expression sigma modulus of xi minus x bar divided by n. You have to take the absolute deviation in each case. For this, you have to take the difference between each measurement and the mean of the measurement, takes its modulus, that is nothing but the absolute deviation. So, find out absolute deviation in each sets, sum that absolute deviation, divide it with the total number of measurement, that is equal to 5, and the answer will be 0.1 ml. You have to use the paper and pencil to work out this problem, and you can simply calculate the average deviation based on the concepts and equations we have learned. So, you will get the average deviation of the set of 5 values equal to 0.1 ml, and your option is option B. Now, this is the second question. Which of the following statements is true regarding sample standard deviation? These are the options. It is always smaller than mean of the data set. It can never be 0. It accounts for variations from mean for a sample of the population. It is independent on the size of the sample. You have to carefully go through each and every options, and you can arrive at the final answer as C option. That is, it accounts for variations from the mean for a sample of population. This is the most correct statement about sample standard deviation. Now, this is next question. Suppose you measured the absorbance of a solution as 0.567, 0.560, 0.565, 0.562 and 0.570. What is the sample standard deviation if the mean of this set of data is 0.5648? So, this problem is to calculate the standard deviation. The mean value of the data is also provided. You are having 5 sets of data here, and you have to calculate the sample standard deviation. So, denominator must be n minus 1. We are taking sample standard deviation. So, these are the options, and the result of the analysis of the result, the final value of the standard deviation of this set of data equal to 0.004, and the sample standard deviation is calculated by using this expression under root sum of xi minus s bar square divided by n minus 1. Once again, remember, the denominator is equal to n minus 1. In the present problem, you are having 5 set of data and denominator equal to 4, n minus 1, 5 minus 1, that is equal to 4, and the result will be 0.004. Another problem is the average deviation differ from standard deviation because. These are the options. It uses difference from the mean. It uses absolute difference from the mean. It is always larger than standard deviation. It ignores the mean altogether. This problem is about average deviation and it's a difference from the concept of standard deviation. This is your option. The answer is option B. It uses the standard, the average deviation uses absolute difference from the mean. That is option B is your answer. Now, we are discussing another problem. Which of the following is not a proper use of RSD? That is relative standard deviation. These are the options. Comparing the precision of measurements, assessing the reproducibility of analytical methods, calculating the accuracy of measurements, reporting precision as percentage of the mean. On careful analysis of these four options, you can arrive at the final answer as option C, calculating the accuracy of measurements. Another problem is here. What is the primary advantage of using average deviation instead of standard deviation? These are the options. It gives a more accurate result. It is simpler to calculate and easy to interpret. It is always smaller than standard deviation. It accounts for outliers more effectively. It is very well clear that the answer is option B. It is simpler to calculate and interpret. Whenever you are comparing average deviation and standard deviation is somewhat difficult to calculate. It requires some more mathematical steps. But standard deviation is difficult and it is very well clear that average deviation is more easy to calculate and interpret. Now, this is the last problem of this module. Suppose you measured the concentrations of a solution 5 times. The obtained data are here. 1.2, 1.4, 1.5, 1.3 and 1.6 milligram per liter is the concentration. The mean value is also provided, it is equal to 1.4 and the standard deviation is 0.14 milligram per ml. What is relative standard deviation as a percentage? So, relative standard deviation, when expressed it as a percentage, you can call it as coefficient of variation. So, you have to compute relative standard deviation and multiply with 100 to get it as a percentage. The answer is option B, that is 10%. So, RSD percentage equal to standard deviation divided by x bar, that is RSD, just multiply with 100 to get its percentage. So, RSD percentage is 0.14 divided by 1.4 multiply with 100 and it is equal to 10%. That all about the present module. In this module, we have give maximum emphasis to the concept of standard deviation, relative standard deviation and recalled the concept of average deviation. That all about the present module. Have a nice learning experience. Thank you.